Today's talk is by a third year PSMS student, Sreyas Adury, on computer aided drug design, mostly about his work in IISER during the last 2 years. Yeah, over to you, Sreyas. Thanks.
Okay. So first of all, thanks to Science Club for giving me a chance to do a talk. I am not a great speaker, so please bear with me while I give the presentation. Also, I wanted to clarify one thing, which luckily Tushar has done already, is that I'm not sure how clear the abstract was. But the work, while it is focused on the general ideas of computer-aided drug design, it is more building towards the work that I have been doing as a part of a project I've been doing in the last 2 years. So it basically builds towards that. And so I think we can start. I will be putting on my video, but do let me know if I lag or something, because I might be using my hands in the middle. Okay. Can you see the slides?
Yes.
Okay. Basically, in this talk, we will be talking about computer-aided drug design. So before we go any further, what do we expect of computer-aided drug design? We want to first find molecules that serve as drugs, and basically the idea of a drug in general is a molecule that can be used to treat usually illnesses or any medical conditions that we know. Also, other important things that we need to do for a program to serve as a drug finding program is to be able to predict toxicity, because we cannot have molecules that work as medicines and are also parallelly toxic. And this will be clarified later as why some drug molecules might end up being toxic. And also, since these are drugs, most often, especially living in a pandemic, it is fairly obvious why we want these to be easy to synthesize, right? If a drug happens to be extremely costly, we cannot really use that very frequently, especially for a disease that might be prevalent. But the most important thing for computer-aided software in general, and drug design is no exception, is that it should be generally applicable to many cases. We want it to be such that whenever we try to have a computer algorithm or a program or a setup that does something, we want it to be applicable to almost all general cases we can think of. And that is the great benefit of doing something computationally. And that is what we want to get from this also. Now, what is drug design in general? Before going ahead, let's look at what drug design does. So when we do drug design, what mostly we are looking at are protein ligand interactions. So why do most drugs involve targeting proteins, and how do drugs interact with proteins? Well, why? I have a few guesses. I'm not really sure that these are objective reasons, but I have some reason to believe that this is true based on what I've been reading. The idea is that proteins always participate in some form in most illnesses. In fact, it's not illnesses. Almost any cellular process is mediated by proteins in some form or the other. And being able to activate, deactivate, or in some way affect those proteins usually allows us a way to control diseases or something. And the other thing is that they are low risk to target. And this also comes along with the fourth point, that biologically proteins are more accessible to external molecules. And this is important because as compared to the major biomolecules in a body like DNA, RNA, and proteins are the most easy to access. They are always outside the nucleus. They are continuously synthesized and continuously degraded. And anytime you have a molecule, let's say, which interacts with a protein, it is very unlikely to harm the cell permanently, because proteins are always constantly synthesized. In contrast, if you use something that would target DNA or RNA, for example, it is more prone to causing greater damage should it go wrong. And another thing which I believe is true, but I do not have enough information about other biomolecules to be really sure, but proteins for sure take up very specific 3D structures. And these structures are very easy to obtain in comparison. This is very useful for computer-aided drug design in specific, because a lot of the structural design, as we will discuss later, really depends on knowing the 3D structure of the receptor proteins. And the most common feature for any drug design, computer-aided or otherwise, is to find a ligand that usually binds to a particular region of the target. So in the rest of the talk, we will be discussing about proteins, but feel free to think of any receptor when we talk about proteins. More often than not, it will be a protein, but it can be anything. So as far as proteins are concerned, these are a few common things which we can achieve if we use computer-aided drug design targeting proteins. One is competitive inhibition, and the other is allosteric inhibition. Let's talk about inhibition first. So what inhibition allows us to do is we can stop a certain protein from functioning, and allowing that to happen. Okay, never mind. So allowing that to happen is very important, because if we have two proteins, we have a protein and we have a molecule that can inhibit it, we can stop a certain process in the cell from taking place. And usually this might involve certain interactions which are very specific to parasites or any pathogens that enter the body. And being able to inhibit these interactions effectively renders those pathogens harmless. In certain cases, there are some pathways in the cell which are not regulated properly, and being able to switch out those pathways or being able to stop them gives us a way to control diseases that follow those kind of pathways. The very less common method thing which is used, but the concept is the same, so I have put them here as well, is artificial activation and simple binding. So artificial activation basically means that instead of artificially stopping a protein, we artificially activate it. So usually this is rare, and I'm not sure why, but I found that doing drug design or any small molecule design in attempt to activate a protein is not very common. However, in theory, the concept is the same. If you are able to find a lot of proteins exist such that if you take a protein and if you are able to find a molecule that can activate the protein, as we will read about allostery, it's similar to that, except instead of inhibiting, it activates the protein, which later brings forward to future reactions. My guess as why the artificial activation is less common is probably because most cellular processes which require artificial activation require you to supply the exact substrate and not any molecule that binds in the active site, because the reaction itself also has some significance. But I'm not really sure on that one either. But another important thing that we can do, essentially using the same concept as we will be discussing in this presentation, is simple binding. Simple binding is when we do not care about any other interactions the molecule might have in general in a living cell. So for example, a very common example which you might be knowing is things like ethidium bromide, which binds to DNA. So when you think of molecules like this, you do not really think about toxicity, and you're okay with having a higher synthesis cost or being difficult to synthesize, because you'll be using them at a laboratory scale, and these will be used more as fluorescent tags like ethidium bromide, and they are used because we want a strong binder, but we don't really care about any other side effects it might have, because we are never going to use them on a living target. I will proceed, but I forgot to say this in the beginning, so feel free to stop me at any point in the talk and ask questions. That is not a problem at all. So take a second. Okay. So before we look at how we do it in a computer, let's just recall the ideas of competitive inhibition and allosteric inhibition. We'll be focusing on inhibition because that is the most common, but like I said, the concept is the same. So what happens here is that a drug competes with the natural ligand to bind to a certain enzyme pocket. So normally what the standard hypothesis, or I think the most commonly understood way of which an enzyme functions, is that an enzyme binds to a substrate, it performs a reaction, and the products leave. And the products usually have much weaker affinity towards the same cavity, and so the enzyme is again free to operate on the next molecule. Also, enzymes are mostly, and this is almost always true, they are catalysts. They themselves are not affected by the entire reaction, and so this enzymes provide a very efficient way to do these reactions. And this is why most processes in the cell are governed by enzymes. Now, what we are going to do here, using competitive inhibition, is we are going to try to introduce another molecule which is going to bind to the pocket strongly, but it is not capable of reaction. So it will never react, and because it can't react, it will stay bound. And there are a few requirements here. We want it because even simple binding and unbinding is usually an equilibrium process. We want the equilibrium to be strongly shifted towards the inhibitor and not the natural substrate. So what we want to try is basically we want the inhibitor to bind so strong that the natural substrate is not able to displace it for a large fraction of the time. So the reaction is effectively slowed down 100 to 1000 fold, and that effectively renders the protein usually incapable of further reaction. But it is very important to remember a few things as we need to know. Firstly, we need to know the active site we are targeting. This is usually not a problem, but there are proteins for which we do not know the active site as yet. The protein structure should be known. but this is something which will be applicable almost always as far as this talk is concerned for any kind of computer-aided drug design. About the efficiency, it's important that because this is an equilibrium process, the equilibrium, according to Le Chatelier's principle, also depends on the amount of concentration of both the participants in the reaction involved. So it also depends on how much the natural ligand is expected to be present in the body. So if you are targeting to block something which is a binding site to something that is extremely commonly found in a cell, you need to find a much more potent drug than something that is not very commonly found in a cell. And done properly, meaning that if this is actually not very well phrased, but what I'm trying to say here is that it is if we have a sufficiently good and strong binder, it is likely to outmatch any natural ligand, because when we are performing, when we are trying to have an inhibitor, we have less restrictions on what chemicals are allowed to be part of the inhibitor, unlike the natural ligands, which are synthesized by the body, and there are limitations on what is available. Let's compare that to allosteric inhibition. So for allosteric inhibition, the difference is that the drug binds to a secondary site. So what happens is that instead of targeting the directly competing with the drug itself, directly competing with the ligand itself, the drug binds to a secondary spot, and the protein changes its conformation because of something being bound in its allosteric site. And now this change happens at the active site, and now the protein is incapable of further reaction. So one of the key problems with not problems, but it's important to have, is that we need to know an allosteric site, and this is even more difficult to find than active site, because allostery is not very common, and even where it is there are a lot to depend on how strong the allosteric effect is, and it is not always that allostery is a 1-0 switch, like it's not always off and on. Many times it so happens that when a drug binds to an allosteric site, it is not guaranteed to change the conformation, and there is a fraction of proteins for which there's a fraction of the protein which changes conformation, and then there are models based on that as well, which try to predict how much of the protein remains active. So this complication is something that makes allosteric inhibition more difficult. However, on the plus side, the advantage is that it is less dependent on how much natural ligand is present, because there is no competition whatsoever. Once the drug is bound, this receptor is effectively no longer the original protein, and there is no competition between the drug and the ligand. So once the drug is bound, the reaction cannot happen. I'll wait for a second. Okay. So before we jump into computers, let us look at the idea of binding free energy. So free energy is what governs the potential of any molecule to bind to a protein. So when we look at any reaction, this is the most common way a reaction happens. This is the postulate based on which we treat enzyme reactions. We take an enzyme and a molecule, here the drug, and it forms a complex. And the delta G of the reaction is RT-ln K equilibrium, and the K, as according to reaction, is the ratio of products and the ratio of product of reactants. So it's basically this. Doing the math, it is important to remember that we do not. Okay, this should have been. Sorry. Yeah. So given that drug concentration is limited, we cannot. This is an important thing to remember when we are doing any kind of drug design, is that drug concentration is low, very low. We cannot expect to have large amount of drug being part of a cell. So effectively, the K equilibrium also determines that when we take a certain given concentration of drug, a very low amount, what is the fraction of the enzyme that is part of the is bound to the drug, and the higher this fraction, the more efficient the drug is for a given fixed concentration, and that is the binding constant or the equilibrium constant for this reaction. And when we compete with a ligand, it is let's not look at like the mathematics per se, but it's worked out here, is that effectively if the reaction is now competing with, there are two reactions which are competing, and one is K for the drug and one is for the ligand, and taking the ratio, taking logs, doing the mathematics, basically we end up with the final expression of delta of the binding energy. The difference between the binding free energy between the drug and the ligand is going to be equal to RT ln D by N. Just taking this to the other side. That means we need the delta of binding to be negative. That is, we want the free energy of binding of the drug to be more negative than the free energy of binding of the natural ligand. And the greater this difference is, the more stronger and more potent our drug is going to be. And that is why computing the free energy of binding of a drug or any ligand to a protein is very important for computer-aided drug design. How do we handle these in a computer? So the key feature, as I just said, is that we need to be able to estimate ligand-protein interactions within a computer. And we use classical force fields as one of the methods. That is what we'll be discussing in this talk, if there are others. Classical force fields are molecular models. What they do effectively is that when we are looking at a molecular interaction inside a computer, we need to be able to quantify how strong, how weak, or what those reactions are going to be. And this quantification is achieved by force fields. What force fields do, however, is that they're classical. They do not have quantum mechanics incorporated in them, or whatever is incorporated is not going to be recalculated when there are any modifications. We assume that the chemical structure of all the molecules in the reaction are going to be intact, which basically means that they would fail to properly simulate any given complete chemical reaction. But that is not a great concern at the moment, because the drugs we are attempting to find or construct will be basically focusing on non-covalent interactions. Now, ideally, if there are drugs that can covalently bind to the protein and render it useless, they will be much more powerful. But we find that even non-covalent interactions, the drugs which we can get, are fairly potent, and finding the right molecules can help us even without having to know anything about the chemical reaction between the drug and the protein, even if it doesn't happen at all. And that is why sheer non-covalent interactions, such as stacking or dipole moments and stuff. Now, we will come back to this concept of atom types, which I will revisit when we look at the algorithm we've been working on. But basically what atom types do is that if you look at a molecule, they are going to categorize the atoms in the molecule into certain classes. And each of these classes have similar reactive and geometric nature. So effectively, when you look at a molecule and you try to break it up into smaller fragments, what is the first thing that comes to your mind? Atoms, right? A molecule will be constructed out of atoms of carbon, nitrogen, oxygen. But this classification is not sufficiently strong, because carbon in a carbonyl moiety and a carbon in aromatic benzene moiety are going to react completely differently to even a local environment, or even if they were supposed to be part of a reaction or an interaction. This is even more noticeable for molecules which are strongly polar, like oxygen, nitrogen, because how these are placed and what is attached to them can greatly change the polarity of these molecules. And that is why instead of categorizing them into elements, we categorize them into atom types, such that their reactivity and geometry is similar. And because we can use this partitioning, we automatically incorporate hybridization as well. Since we are anyway not partitioning based on elements, we can implicitly also take hybridization as one of the parameters of partitioning. And so we require now that if any two atoms have the same atom type, they necessarily must have the same hybridization as well, among other things. So notice that this is not a two-way rule. So it is not that if two atoms have the same hybridization, they are the same atom type if they're the same element. It might happen that a carbonyl carbon and an acid carbon are actually different altogether, though both are sp2 hybridized, as is aromatic carbon. We will come back to more details into why this is important later, but this is an important concept to remember as far as force fields go. And with that, immediately we come to the idea of molecular geometry. When we are trying to predict whether a certain interaction is feasible or not, we want to know whether the molecule is in a stable geometry when it is bound. So when a molecule comes to bind into a protein cavity, it does not take its most stable structure as though it would have in water or in vacuum. It must make certain changes to its structure, usually to the dihedrals, as we'll discuss. But mainly the structure slightly takes a change from its original base structure. And to know whether this structural change is worth it, whether it is worth compensating for the amount of interactions that it will get from the protein, because the net stability of a drug, whether when it binds into a protein, is going to depend on the interaction with the protein and the stability of the molecule in its bent state as well. If you are able to get a very strong polar stability by turning the molecule in such a way that its dihedrals overlap into an eclipsed state, for example, it becomes a question of a tug of war between the two forces, and we will end up with whichever is the more dominant. And to be able to calculate these kind of things, we need to know what happens when these parameters change. And we'll come back to these parameters again in terms of de novo atom molecule generation. But as of now, these are parameters which have an equilibrium value, which is what you would ideally expect the molecule to take, assuming there is no other external pressure on it, and a force constant which tells you how much energy would require it to change by a certain amount. And these force constant are different for each of these three things. Usually they fall under classes of lengths, angles, and dihedrals. And it's as almost everybody studying chemistry would know, bond lengths are the most difficult to change. And that is because bond lengths are very rigidly governed by the elements holding it, and it is not, bond frequencies are also very, very specific, as you would know probably. Causing a bond to stretch by even a small amount, it requires a lot of energy. Bond angles are more flexible, but even not so much. The most common changes, as you will observe, will be in the dihedral angles. And before I explain this further, I think it's important to explain the concept of a dihedral. So if you remember studying in 12th class, or I don't know if this has been covered anywhere else, but this is how eclipsed and staggered states of butane look. And you would know that when they are eclipsed, it is most unstable, and when they are staggered completely, it is the most stable. And this is the energy profile of a dihedral. This angle is the dihedral angle. I have attempted to make the same figure here as well. So I've taken dichloro ethane, just because drawing butane would make this extremely cluttered, because they would form methyl groups. But basically the idea is that this length is fixed, this angle is fixed, this dihedral is fixed. And what is important, as I wanted to also mention, is that when we are considering binding, these local minima are also as important as the global minimum, because firstly, this difference is sufficiently small. Okay. So just one second. So this difference is sufficiently small, and also the local minima is also pretty deep as compared to the two transitions that it would have to make if it has to go into the global minimum. So these are equally important as well. And with that, I think, yeah, before we get to this, any questions? I'll hold for a second. Okay. So like we wanted to discuss, non-bonded interactions were essential to model in ligand protein interactions. But these non-bonded interactions have to be modeled in a computer, because we cannot exactly calculate the non-bonded interactions, partially because it's computationally very expensive to do each time. And that is why we use certain parameters to fit these interactions to the best of our ability. And we find that these models perform fairly well at doing interaction, at calculating interaction energies, as long as we had discussed, no reactions are taking place in the middle. So if we start with a protonated molecule, deprotonation is not possible, for instance. However, as long as it's going to stay protonated at that pH, the interaction energy this calculates will be pretty accurate. And the two potential energies here that will come in the subsequent slides will be elaborated is the Lennard-Jones potential and the electrostatic potential. So what the Lennard-Jones potential attempts to do is it tries to model the dispersion forces, which are usually non-polar, and they are going to be modeled by more dominant in things like non-polar things like alkanes and alkenes and things like that. The electrostatic potential is for the more polar based interactions. And now notice that these models do not have a specific term for specific interactions like hydrogen bonding or pi-pi stacking. So what they do is basically they incorporate these parameters in such a way that those independent contributions also come into part as one of these two potentials usually. And the thing is that the hydrogen bonding usually is mostly governed by electrostatic potential, and the Lennard-Jones potential usually takes care of pi stacking and things like that, partially also given up to a small polarity, because pi-pi stacking is directional. Okay. It's also important, before I go to the exact form of these potentials, hard sphere cutoffs are usually kept at very small distances to ensure that there are no physical clashes. So we know, and we will see soon, that even Lennard-Jones potential and in real life show that two atoms cannot come really close to each other without extremely compensating on their energy, and it becomes extremely unstable to bring atoms too close. Now, it is obviously governed by the Lennard-Jones potential, which will automatically discourage this thing, but hard sphere cutoffs also give us a certain advantage in the sense that it reduces the amount of computational effort required because hard sphere cutoffs just need to make one check whether they are close or not, rather than computing an entire expression for Lennard-Jones potential, which is pretty complicated. And this is exactly the total form of the Lennard-Jones potential. It includes basically, we don't need to look into the mathematics, but the important parts are it includes a very short range repulsive and a long range attractive term. And the reason I'm saying short and long range are because of the powers, the raised to 12 and raised to 6 part, and the radius. The r is the radial distance, which is in the denominator. So as r goes to 0, this each of these fractions go to infinity. However, the positive term will go to infinity much faster than the negative term because of the higher power. Similarly, at longer distances, this fraction as r become as sigma by r goes greater than 1, what happens is that this term is going to be less than 1, and raising it to a higher power will make it smaller, and effectively your potential is going to be negative. And this is what is the long-term attraction, long-range attraction term. And as the potential goes to 0 at infinite distance, and this is required for almost any potential we are going to look at, and this is a mathematical result that there is a minimum at r equal to 2 power 1 by 6 of sigma, and this is not significant directly, but we will look at why it is important. The electrostatic potential is what you would expect normal electrostatics to look like in physics, is k q by r, and it will use the same form as the simple point charges, but the charges used in the formula are polarization charges and partial charges, but the polarization, such as in special polarizations like hydrogen bonding or usually any other kind of extra polarizations, like there are hydrogen bondings of different form, like nitrogen based hydrogen bonding, oxygen based hydrogen bonding, and such polarization terms are also incorporated. It is not purely partial charges only that are incorporated into this, but the net effect is that it accounts for the polar terms in the interaction. And there is the important point here is that there is no non-trivial minimum. If q1 q2 the product is negative, then it hits infinity, minus infinity at r equal to 0, and it goes to 0 at infinite distance. If the product is positive, it hits plus infinity at r equal to 0 and goes to 0 at infinite distance. But either way, there is no non-trivial minima for this system. So this is where the Lennard-Jones potential and the sigma value become important. If you were to have a positive and a negative charge, if there was no other potential to stop them, they would basically collapse into a single point, because that is the most stable place to be. But that's a bit then. So when we look at non-bounded potential functions, we have two potentials. One is the Lennard-Jones potential and one is the electrostatic potential. And the Lennard-Jones potential is the potential that models the non-polar interactions. It has a short-range repulsion term and a long-range attraction term. And the attraction, repulsion, and the short and long range are governed by this power and the sign. At very, very short range, especially when r is less than sigma, this ratio is going to be more than 1, and raising it to a higher power makes this increase much more than the sixth power. And so the net potential is going to be positive. That is, the system will be unstable. Similarly, if we do this for longer distances, it will be more stable, because this ratio will now be less than 1, and raising it to power 6 is going to be the more dominant factor of the two. The potential goes to 0 at infinite distance, as we expect all potentials should, because they are interaction terms, and we do not want any interactions when the protein and the ligand are very, very far, or any two molecules are very far. And there is a minimum at 2 power 1 by 6 sigma, which is a mathematical result, and we'll discuss the importance of this minima in a while. The electrostatic potential is what is the obvious physical electrostatic potential. It is k q by r, and like simple point charges, but the partial charges which are used are those with polarization incorporated into them. So we do not use what are in the classical sense just partial charges. They are charges fit into the model in such a way that the polarization and the hydrogen bonding and such other terms are automatically incorporated, and the interactions are calculated more accurately. For the electrostatic potential, however, there is no non-trivial minima. All the minima happen either at 0 or infinity. If q1, q2 is positive, then you hit infinity at r equal to 0 and 0 at r equal to infinity. But when they are negative, you hit minus infinity at r equal to 0 and 0 at r equal to infinity. But in no way in the middle do we have a minimum. And so that is why this Lennard-Jones potential and other hard sphere potentials play an important role. Because if you take two atoms which are oppositely charged, the most stable position for them to be is to converge into a single point if electrostatic potential was the only potential governing the motion. And that is why we look at the form of the Lennard-Jones potential and the electrostatic potential. So as you can see, the Lennard-Jones potential dominates significantly at shorter range. Here we have taken sigma equal to 1. But basically what is important is that at a shorter range, you can clearly see that the Lennard-Jones potential significantly dominates the end. The net potential energy almost follows exactly the same trend as the Lennard-Jones potential at the long range, at the short range. But at the long range, you can see that the energy is now coming slowly closer to the electrostatic potential, and the Lennard-Jones potential dies out much faster. And that is expected because dipole-dipole interactions are usually much more stronger than van der Waals interactions. And that is why they last longer, or they still contribute at larger distances. The net potential energy, and this is why I said the position of the minima matters, is that it is more frequent, and I have tried this for different values of sigma also, not that I could put them here, but it happens that this minimum position is very close to the position of the minima in the pure Lennard-Jones potential case. And this is where you would like, ideally, in the absence of any other forces, for the atom to be. But of course, since we are going to look at an entire molecule and not just one atom, these potentials are going to be somewhat traded off for the net interaction energy to be high. And finally, the most important thing about force fields is that these potentials are summable. So what we basically do is that if you want to look at the total interaction energy between the ligand and the protein, the model is such that you can sum up the potential energy between all the atoms of the ligand cross to all the atoms of the protein. And that is going to be your net interaction energy. And that is what makes computation extremely simple, especially when you want to do some calculations on a large number of molecules or very quickly on a given molecule. So we want to see how to design new drugs, but before that, we know that force fields allow us to calculate interactions, as we've seen. But we need to know the 3D structure of the exact position of the molecule. This is very important. We cannot calculate potential energy just by a protein and a ligand. We need to know exactly how the ligand is going to bind to the protein in reality. And only with these position, or this what is called a pose, can we tell whether the potential energy is good or not. And to find the pose is the most difficult problem. We can, for any given pose, we can calculate the interaction strength, but the pose that is going to show up in experiment or in real life is going to be that pose which has the best interaction energy. And to find the best pose is the problem. And this one most common way to do it is molecular docking. So what it basically does in docking, and there are different algorithms for this. There are different ways in which this is achieved, and we will mostly not discuss them here. I can answer questions later, but the idea is basically this. It starts with taking a molecule, taking a protein, and we assume, for the sake of the calculation, though this can be relaxed, that the protein cavity does not change shape when the molecule is bound. And then we try out a large number of possible configurations. And as we had discussed before, the configurations of a molecule depend on its dihedrals, angles, bond lengths. And these parameters are treated, these forces are known. So you try out a large number of possible conformations the ligand can take, and you try to place it at different points in the protein. And this is done by usually a translation step, followed by a lot of rotations, and then again a translation followed by a lot of rotations. This basically, rotations have angle and dihedral, and this basically achieves the effect of trying different positions in the protein cavity and trying a large number of conformations for each position tried. And then you calculate after each rotation an energy. And you do this and you finally report the minimum value usually and say this is the most stable pose in which the drug is going to be bound to the protein. So my guess is that in reality, this is exactly how the drug would be. And assuming this is true, this is my energy score. This is the free energy that the drug would give if it were bound in this pose. And this is exactly what is reported by the process of docking. And this process will keep coming up in many other computer-aided drug design procedures. That is why it is important to discuss docking. I'll pause for a second. 2 questions.
I think there are a few questions in the chat box. Do you want me to read them out?
Okay, sure.
Okay. So both questions from Swastik. First one, slightly confused about Morse and Lennard-Jones potential. Both describe the same system, right?
Okay, Morse and Lennard-Jones. Is that the comparison?
Yeah.
Okay. I do not remember the exact form of the Morse potential, but I believe the form is slightly different. The trend, this curve, the shape of the curve, which you see, this kind of curve is the Morse potential as well. But if you look at the functional form, it is not the same. I think it involves an exponential term, whereas the Lennard-Jones potential uses just polynomial terms. And I am not very certain of what the Morse potential actually describes. I think it describes the interaction when two atoms are far, but when they are bonded. While Lennard-Jones potential describes the interaction when they are not bonded.
Okay, the second question is also, could you highlight the difference between dispersion and polarization?
Okay, so what I meant by dispersion forces were those standard potentials which act in almost every system, even if they are non-polar, like those van der Waals dispersion forces in alkanes and alkenes. That is what I meant by dispersion forces. Polarization and polar forces are those which, like hydrogen bonding or even dipole-dipole interactions, like in water, alcohols, or any polar molecules. So that is what I meant by polarization and polar interactions. Does that clarify?
Yes, it does. Thanks.
Okay, so shall I continue? Okay. So now we hit let's say, crux of this topic, de novo drug design. So drug design comes in many flavors actually, and there are a lot of ways in which we can find drugs. You can take what is going to be the focus of this talk, de novo drug design. You can have screening from a set of known molecules. You can have analog design and similarity based design. So we will be focusing almost entirely on de novo drug design, though in the end we will touch upon this idea slightly, but we will not go into a lot of details about it. So what de novo drug design looks like is this. The molecules are generated in the computer completely afresh. The program has no knowledge of any known ligand, known binding cavity, known binding molecule or anything as such. It only has information about the 3D structure of the protein and the binding cavity. It does not have any information about any known prior molecules. And the program attempts to find or construct molecules using some algorithm, such that these molecules will have a strong interaction energy to the cavity that we are looking at. And let's look at first fragment-based de novo drug design, because we will also be just touching on this topic. What fragment-based drug design does is basically, instead of you having to take the effort of completely reconstructing a molecule from scratch, what we do is we use a template of fragments, and we have an entire database, and a lot of databases are available for this. And what it does, it commutatively picks up fragments from the database, joins them, and for each of these fragments, there are positions where they are allowed to join. For example, most common rule is that they can join anywhere where there is a hydrogen atom. So, for example, this is the combination that is happening here. This is the combination that is happening here. And this is how these different fragments combine, and you get a final molecule. These molecules are then, I will describe the procedure later, but the fragment databases there are quite a few, and also the possibilities of molecules grow exponentially with every added fragment, because every added fragment can now bind to every position of every other fragment that exists. And so you have a large set of options to try out. And one of the good things about this is that the molecules are going to be more easy to be drug-like molecules, and we'll discuss why this is important. But in general, given that the fragments come from drugs, they're more likely to be drug-like molecules. The disadvantage, however, is you have an extremely biased samples. You only have fragments which are known, parameterized, known to work for some reason, or usually very commonly they're part of drugs. So it does not allow the program to explore newer spaces very easily. But either way, this is the final protocol. You get the 3D structure. This is almost going to be common everywhere. You plot the fragments. This is actually not supposed to be here anymore. And you commutatively generate a large number of molecules using these fragments. And I will talk about empirical filters towards the end. But there are some empirical filters that tell us whether this molecule is likely to be a good binder, likely to be a good drug, before even calculating any energy or any mathematical terms. And after they pass through this filter, quite a few molecules pass through these filters. And then we dock all of them, as we had discussed the protocol. We take all of them, put them onto a protein structure, and try to find the best pose, find the energy. And we find a ligand lead, as it is called, which basically means that this is the ligand which is likely to be a good binder. And then there are attempts to improve the lead molecule. This is optional. Not every fragment-based protocol does this, but this happens quite frequently. And we do this repetitively until the score is satisfactory. And the score is effectively the computer's prediction of the strength of binding. That is how strong the drug is going to bind. And usually you keep thresholds with prior knowledge. You know that we need at least a certain amount of binding affinity, a certain free energy, a certain dissociation constant, or something like that. And using this prior knowledge, we stop when we think that we have found a good molecule, and then we try it out either in experiment or more rigorously using more sophisticated theory, now that we have much lesser number of molecules to actually try out, rather than try out this huge set of combinatorially generated molecules. The attempt to improve is slightly different from combinatorial generation, and that is why it is separate. So what this does is similar to analog generation, and I think I will discuss it right now. So what it basically does is it takes the molecule that you already have, and it tries to improve upon it by either adding fragments to the sides or adding small modifications to the sides, like converting alcohols into ketones or something like that, and making slight smaller modifications. And that is why it's also important that after improving the lead molecules, you need to again pass it through the empirical filters. I think the flowchart might not be exactly perfect, but it is important that after this happens, you need to first pass it through empirical filters like drug likeness, because any of these side modifications might again affect the drug, the likelihood of it being a good drug. And you want to ensure that that is not the case. And then you usually repeat it, score them, and again come back to the score, see if it is better or if it has improved. Another stopping criteria, usually not successful, is when the score is not improving any further, but you have not reached your aimed threshold. That is also when the program can stop. Now we come to atomistic de novo generation, and this is kind of the focus of the project that I have been working on for 2 years. And the alternative method, which is important, is to generate this molecule atom by atom. And why this is very difficult is that you cannot join any elements and attempt to come up with even a stable molecule for a drug. It is important that these connections have to be stable, viable, and the molecule should be able to stay stable even outside a protein. And more importantly, they should not be volatile. And given that we have a molecule, how do we get parameters for energy? So this is something I should have discussed with the fragments as well, is that when you look at these fragment libraries, the parameters for each fragment are easy to get because the entire fragment is present. So it's easy for you to tell what parameters toluene would have in general. And the slightly modified toluene would have similar parameters, if not the exact same. But when you add atom by atom, if you add a carbon and you add a double bond O, you have severely changed the chemical properties of the carbon after you have added an O with a double bond or even a single bond. But this is where we use the atom types to our advantage. So instead of using elements, we don't say that we have a carbon bonded to a double bond O. We can only have a carbonyl carbon as an atom type that is now bonded to a double bond O oxygen. And this is what makes this feasible. And before I elaborate this any further, I think I should explain how atom types work at this point. So when you're constructing an atom, molecule atom by atom, it is really important to understand that what parameters we have taken, since we are now constructing it atom type by atom type, the parameters which we are using for this atom type should be viable and valid. So what we do is that during the construction, we ensure that if we have taken a certain atom type, so we have now a set of bins, let's call them, for each atom kind. And one of them is going to be a carbonyl carbon, one is going to be an acid carbon, one is going to be a benzene carbon, one is going to be an alkane carbon. And if you pick up a carbon which is part of an alkane, it cannot bind to an oxygen atom with a double bond, because that is not something that an alkane carbon is allowed to do. And we will discuss this when it comes to rules. But as of now, let's just look at the geometry problems. It is not easy even with atom types, because the first important thing is we need to have geometric constraints in place. And atom types, however, help us there in the sense that they give us information about the local neighborhood and they tell us the hybridization. And this is very important. Geometry is governed, as we know, entirely by hybridization. And if we know the hybridization, we almost certainly know what geometry this atom will hold in 3D space. And that is what is going to allow us to construct it in 3D. And when we come to the algorithm, that will be explained. But the algorithm works and it keeps adding atoms until either we have a certain size requirement which is met, or all valencies is satisfied, which is rare, or vacant valencies are physically obstructed and you cannot add any more atoms. And this is very common because now you will notice that in any generation, if you are going to add atoms to a protein cavity, it is very likely that after a certain point, there is a free valence right there, but there is no place to add an atom because it's going to clash with the protein. And this is true for any 3D confined space construction that you would do, not just for chemistry or atoms. And this is one of the problems that we might incur. So the algorithm looks for either of these two cases. Either it successfully generates it, or it fails to and it retries. And because of the computational speed available to us today, we are able to generate a large number of molecules, and I mean like lakhs of molecules to try out, and a lot of which are rejected. A few are accepted, and the rules we will look into. We will look at them in a future slide. But as of now, let's look at atom type rules. So what I was speaking about as atom type rules was what I meant when I said that when we take atoms from a single bin, we need to ensure that it satisfies the properties of the bin it was picked from. So if you look at a carbonyl carbon, if I tell you that a molecule has a carbonyl carbon, you would automatically expect that it is bonded to an oxygen by a double bond. And this is the exact kind of rule that we impose on our molecules as well. So when we take an atom and we say that it belongs to a certain type, we enforce all the rules on it that require it, so that when we finally satisfy all these rules, they're so finely tuned that the parameters that would act in real life are going to be very close to those parameters which for the atom type from the bin from which we have taken it. And we know that for force fields, this is already done very well. So force fields have, like we had discussed, carbonyl carbon parameters ready. If we ensure that a carbonyl carbon is going to be perfectly generated as a carbonyl in the final molecule, the parameters are going to be same. And they ensure mainly, like I was discussing, accurate valencies, because hybridization also decides an element and hybridization together decide the valency. They also decide the rational geometry, like we discussed, and some of the important things like aromaticity. You cannot have a benzene carbon that is not part of a cycle, right? That is not something that is allowed. And these are rules these kind of rules are empirical rules which ensure that the molecules we have are chemically sensible. And that is basically the description that I wanted to go through. And this local neighborhood is what is used even in force fields to parameterize atom types, and we have taken advantage of this feature of force fields, that they use the local neighborhood to parameterize the atom types. I think before going to geometry, I should stop. This was a bit. Are there any questions? Okay. So I'll assume not, and I'll proceed. I am audible right now. I'm starting to doubt my network connection.
No, you're audible.
Okay, thank you. That's fine. Good. So that is with the rules. But now we come to the next question. Where do we add those atoms? For fragments, this was a very small problem because almost the entire geometry of a fragment is fixed. You have very few options to tweak, and most of them are going to be viable if not perfect. For atoms, you cannot place them everywhere you want. There are certain rules. And this is where I said, as I had said, we would come back to the idea of length, angle, and dihedral. We are dealing with 3D space. And any three constraints are sufficient to decide a position uniquely in 3D space. And we use, in our program, bond length, bond angle, and dihedral. So if for any atom, we know the length to the first atom it is bonding to, the angle with any of the atoms, consequent atoms, and any one dihedral angle in the entire molecule of which it is a part, we can uniquely say this is where the atom should go. Sometimes, however, like we had discussed, multiple dihedral values may be allowed. And this is what I was trying to say. So dihedral here was dihedral of 60 degrees, 180 degrees, and 240 degrees are all favorable. So it's not unique, but we can guarantee, however, okay, sorry. So we can guarantee, however, that we get a very small number, roughly at most about 6 to 8 positions to try out. And we can trial all those possible positions in that case. And this requires some sampling, which we will not be discussing in this talk because it is too mathematical. But basically, it almost uniquely determines where to put the atom. And that is what we are going to use. And how do we know these three parameters? Again, this is again where atom types help us. Atom types have well parameterized length, angle, and dihedral, and we use these exact equilibrium values for placing the atoms when doing the construction. And you can see that if, let us say, this is the fourth atom we are adding. This is the atom to which it is going to be added to, and this is the molecule we have generated until now, or we have constructed until now. It has three atoms, and the first parameter is the length, that is r vector. The next parameter is going to be the angle. The magnitude of r is the length. The angle is going to be this angle. And finally, the dihedral is, I cannot show it in this 2D picture, but effectively it is going to be the angle between the planes here and here. I think I have a better figure somewhere. There. So this is how we are going to place the first. So, however, this still leaves us a few questions, and I can explain this. Firstly, where do we put the first atom? Where do we put the second atom when a lot of possibilities are still there? The problem is the first three atoms. After which, of course, we have three constraints on which we can exactly decide the positions. But placing the first three positions still requires some amount of trialing. And for the first atom, the only constraint we know is that it has to be part of the active site. We don't want a molecule to be growing somewhere all around the protein. So we put it randomly at any part in the active site as long as it does not physically clash with the protein. And here again, clash has both meanings. A, it has to be stable in terms of potential energy, and B, we also use the hard sphere cutoff to ensure that it doesn't clash in the classical sense. The second atom has only one constraint. It has to satisfy the bond length requirement. I'm assuming this was a carbon-carbon bond. So this is a 1.54 angstrom sphere. And anywhere in this entire sphere is a valid place to put the second atom. Now, for the third atom, you have the length constraint automatically, and you have the angle constraint. This produces a pseudo cone, and the rim of this cone is basically all the positions that are allowed. It should be easy to see that because this is a right angle for the cone. This is a right angle. So you will find that this angle, as it is turned, it's hard to show in 3D, but I hope you are able to imagine that for a cone, all of those positions on the rim are going to be at the same length and will have the same angle over here. And that is the cone, which is also, for all practical purposes, an infinite number of positions to try. So it's not easy. However, now when we add the dihedral requirement, we have only one position, technically two, but because dihedral is not symmetric, basically a dihedral of 0 and a dihedral of 180 are different. So effectively, we have very few allowed positions to place the atom. And you can see how adding one more constraint automatically reduces the possibilities from uncountably infinite to finite. And that is why we do not have a problem about construction after the fourth atom and beyond. But how do we place these previous atoms? And I think that is where we look at the choice of position. And we will not be discussing this in great detail, but the first important thing we need to look at is that we have a choice. And when there is a choice, we need to look at something else that we are trying to optimize with respect to this choice. Because if we had no choice, then the entire process of doing this is moot. Because if there was only one possible outcome, then the entire construction is meaningless. What we want is that there are a lot of possibilities, and we want to sample from these possibilities in such a way that the final construction is going to optimize the interaction with the target receptor or protein, basically in this case. And that is our great requirement. I mean, that is the entire point of drug design, right? We want the drug to be very strongly bound to the protein in the end. And because of the great advantage of force fields, we know that the interaction energies are totally summative. So even if I'm going to add an atom type right now, it is not going to affect the energy of any atom I would add in the future. And the atom I added already make no influence on the potential energy change that this would cause, because they are summed and independently summed. One way to do best interaction is to use a greedy algorithm, and that would be basically that you take all possible positions, or you sample from the all possible positions randomly, and you pick the one which is most stable. However, this has certain problems. The main problem is that choosing a position for an atom essentially dictates the positions for many other atoms. Especially from fourth atom onwards, we have seen that we have very little choice where to put it. And if we are going to be greedy with the third atom, the problem might be that the entire molecule, when looked at in the large molecule level, might not actually be favorable. For all practical purposes, we might even not have place to put the remaining atoms, just because we were greedy for the third atom or the fourth atom. But we cannot again try out every possible position in a rational amount of computational time. So what we need to do is find a method to sample the space in an optimal way, so that we are going to find the more stable options more frequently, but yet we are not going to leave out options which are immediately not obvious. And this is what is bias sampling. And in the interest of time, I think I will not be discussing bias sampling in this talk. But essentially, the idea of bias sampling is that when we are sampling through a set of possibilities, we are going to look at those possibilities which are going to be leading to more energy, more stable energy, more frequently, and less stable energy less frequently. And this frequency is determined in terms of probability, which is a function of the energy. And I think rather than elaborate it, I should leave it at that. I can answer that in the questions if you want more details, because it will take time if I start explaining beyond that. But before we go beyond bias sampling, this is something which we have incorporated in our program, but it is a very generic tool in almost every computer software, not just drug design. The idea is that when you have a structure, a position of a ligand in a protein, you want it to be in its energy minimum, the most stable form possible. But almost all forms of random sampling will never give you the exact minimum. And that is why we use systems like conjugate gradient or gradient descent to perform energy minimization. And one simple intuitive way of understanding this is rigid body dynamics or simple physics, and that is something that we would have studied in 12th class, is that when any rigid body is subject to forces at different points, the motion is governed by Newton's laws of motion. And the motion is basically one resultant force by which it will translate, and a resultant torque by which it will rotate. And if you follow the trajectory of these forces at infinitesimally small amounts, you will find that it will lead to the energy minimum. And this is the idea behind gradient descent as well. And we obviously have an easy way of computing the forces. We know the potentials according to the force fields. The gradient of the potential is the force. So we know all the forces. And because we know all the forces, we can take any molecule in the protein cavity and subject it to the exact same treatment as Newton's laws of motion. Except we do not keep momentum, because momentum is what allows the system to maintain its energy. But what we are trying to do is trying to take the system to as low an energy as possible. So at each step, it's quasi-static. We move it a little bit, little bit, little bit, and each step, because we are following the direction of the force, which is the negative gradient of potential, we are essentially reducing the potential. And finally, we will reach a point where the potential doesn't change a lot, and that is the minimization. And that is how energy minimization is done. There are more rigorous ways in which, instead of treating the molecule like a rigid body, what we treat it is that we allow each atom to move independently of the others, and we include the force field parameters of bond length, angle, and dihedrals, and we allow these forces to take place as well. And now again, as we had discussed, it becomes a tug of war between the internal forces of the molecule and the external forces of interaction with the protein, and the best trade-off is achieved. And this is exactly what we want, and that is what minimization will achieve. This is also done for docking very frequently, because when docking generates a large ensemble of random positions, it is not guaranteed, and it's almost always never going to find the best pose by sheer random generation. What it does after that is a quick optimization. There are large number of minimizations, not just gradient descent or conjugate gradient, but one of the energy minimization algorithms will be used to get the final pose. I will stop for questions, I guess. Okay. I'm assuming there are none. So, fine. And this is just a snapshot. This is the final molecule that has been constructed in a protein cavity, for an example. And this is how the algorithm goes. This is probably going to be fairly straightforward after the discussion, but the first atom is placed randomly, so it's placed here. The second atom could have been placed everywhere, but this was the selected position. The third atom, now, because looking at this molecule, we know that the atom that was chosen here would have been an aromatic carbon atom. So it has no choice but to keep the geometry of an aromatic carbon atom. And that is why you will notice that these three atoms have a 120-degree angle between them. And more importantly, you will see here is that the entire thing is planar. And this planarity is achieved because of the same three-dimensional rules imposed on it by the force field. the side modifications are now slowly added, because now we have completed the first phase of the construction. Now all of these atom types are aromatic, and the aromaticity has been achieved. The carbon atoms are all what we would call satisfied, in the sense that there are no force field rule requirements that any longer are pending. This is sufficient to ensure aromaticity. So now we are going to make sidechain modifications to make the interactions better. But we have complete freedom with these. So here, I guess some atoms would have been tried out, and the alcohol was what was finally chosen. For this, we chose CF3. Looking back, we know that is a trifluorocarbon. And here is where another critical choice is made. This nitrogen which is chosen is an aromatic nitrogen atom, and that is what again forces the rest of the algorithm to ensure that it completes its aromaticity one way or the other. And finally, the rest of the side chain modifications happen as usual. And notice how the carbonyl carbon that was selected here necessarily adds a carbonyl oxygen, and the generation is complete. And this is the final molecule. This will be scored using interaction energies, and depending on our requirements, this is either binned as good or bad. Now we look at more general things beyond my project work itself, but what other things exist in the world of computer-aided drug design. One thing is the generalization of this protocol to fragment-based growth. So the entire algorithm which I have described is fairly applicable even for fragment-based generation, with a few exceptions. Firstly, the fragments are treated as rigid parts. So all the trying of positions of 1 and 2 and 3 atoms are not really a thing, because you do not have to add 1 or 2 atoms at a time. You usually add fragments which have at least 3 to 4. And the rules for the fragments are weaker, because when we have the fragment-fragment connections, the atom type requirements are met in the fragment itself. If you have an aromatic carbon that you're adding, most likely the entire fragment is already aromatic. So you do not have any requirements that you have to satisfy when you're picking the fragment. The only requirement you need to satisfy is the valency condition, that you do not have more valence than is permitted. Usually that is the only thing. And the last difference is that when we pin together fragments, we use the angle in which the fragment is placed. For example, I think it might be easier to go to the fragment generation. I'll be pretty far back actually. But yeah, it's easier to look at this. If you look at this, it is easy to look at this angle. You can see the twisted angle, right? It's easy to just use this angle as a parameter rather than look at dihedrals or angles or bonds or any other. Bond length is of course a necessity, but this is the only angle you would probably be considering at this point, because this automatically determines where the rest of the fragment goes. Finally, fragments. Yeah. So finally, that is how fragments are constructed. And depending on whether the fragment, some algorithms do it like our atomistic algorithm, where the fragments are pieced together inside the protein cavity. Some algorithms piece them out separately in vacuum and then dock the molecules. Either way, the rest of the algorithm is fairly the same. And now we look at what other factors we should consider in computer-aided drug design beyond just interaction energy. They need to be of course, the first requirement was strong binding, but we also need them to be biologically safe and require intake of only small doses to work. Now, the requirement of small doses is handled by usually assuming competitive inhibition, the strength of binding. But biologically safe is something that we cannot be sure of in a computer. And this is something where I believe artificial intelligence or machine learning are likely to do much better, because they are better at grasping patterns in molecules, which are more difficult to find in general. And toxicity is not something that can be objectively calculated based on some physical parameters, because how the reaction happens in a body is not governed by those physical parameters alone. The major factor required for, as I had already discussed, that if you take a drug and you know that it is toxically safe up to a certain concentration, you need to ensure that your dosage is going to keep the concentration of the drug below that concentration. And that also is going to be governed by total binding free energy and the difference between the natural binder and the drug, as we have discussed. If your natural binder is not strong anyway, you might not need a very potent drug, but you need a more safe drug in that sense. You will be able to go for more safer drugs. And finally, when possible, drugs should be easily synthesizable. There are a few programs, again in machine learning and AI, such as IBM's reaction, which are trying to use machine learning and AI to predict synthesis pathways from known or easily available raw material. But that is still a problem that hasn't been perfectly solved. But there has been great progress. I am not really aware about the great developments on machine learning, so I am not delving into the depths in that. Also, another thumb rule, which a lot of people have come up after seeing a large number of drug molecules interactions, is what is commonly known by a lot of people as the Lipinski's rule of five. And this, I have basically taken the statement right from Wikipedia, is that you cannot violate more than one of the following criteria. There should not be more than 5 hydrogen bond donors, no more than 10 hydrogen bond acceptors, the molecular mass should be less than 500 Dalton, and the octanol water partition coefficient should not exceed 5. What the octanol partition water coefficient is a physical quantification of the non-polar nature of the drug. The more non-polar it is, the larger fraction of it goes into octanol. The more polar it is, the larger fraction goes into water. And this logarithm of the concentrations is used as a log p value, and it is the octanol water partition coefficient. Either way, it is important. This is what I meant when I was talking about empirical filters, if you remember. So when fragment-based generation, or even in atom-based generation or any other newly made generation, this is a good rule of thumb filter to look through at molecules that are going to be likely to be at least less toxic, even if they are not easy to synthesize. And that is why these kind of rules are automatically tried and implemented in many algorithms. But, and this is something that even Wikipedia accepts, there are quite a few exceptions to these rules. So it's good to follow these rules, but it's not the holy grail. Now we look at another protocol called virtual screening. So virtual screening is pretty similar to docking. It is basically most commonly docking. But the idea is that instead of taking a newly generated ligand, we take a large database of known molecules, which are potent drugs or usually safe molecules to intake, and we try to dock them all to the active site of the protein. And we try to find if any of these molecules itself can be repurposed to the purpose we are looking forward to. Because it is potentially possible, and it has happened quite a few times by either happy accident or some great intuition of the person who has used it, that many molecules that were already drugs for another cause or another reason altogether happen to be good binders to the problem at hand, and they have been able to serve as potential drugs. And virtual screening really relies on this great strength of computational power today, because it requires you to dock, which itself is a very memory intense and computationally intense process, a large plethora of molecules. However, it has shown some use till date. And sometimes it's also useful if we have no information. This is one way to dock everything. But if you already know some ligand that is bound, there are some common ways to improve your search. Rather than looking at all the molecules available, you filter molecules that are going to be similar to the known binder. Or you can filter molecules which you know, if you know the reactive moiety. Like for example, many times penicillin, you know the part of the molecule that is very important for the reaction. Or for any other, many drugs, you do know what is most important for the drug to function. So you keep that, and you look for molecules which have that common part, but other variations exist. And then you try to dock those molecules. And you can also use other empirical parameters to reduce the size list. And one example again comes back to Lipinski's rule of 5. This is usually not very significant if you are going to pick an already known database of drugs, but this can also be done on a database which is just set of synthesizable molecules, in which case empirical parameters are a great help. And I'll wait a second again for questions.
Okay, I think there is another question in chat box.
Sure.
Is the choice of second and third atom done by computer or through human intervention?
No, it is done by the computer. And what it basically does, I think I should go to the 3D to explain it better. Yeah. So the choice of the third atom basically is that this is the entire set of possibilities. What the computer does is it picks random positions from this entire rim of the cone, ensuring that they're well spaced at least so that you get a good sample of the entire thing. And then it calculates the interaction energy, assuming if the atom were to be placed there, what is the net gain in the enthalpy of the interaction with the protein. And this is calculated for each of those positions. Now at each of those positions, whichever is the most stable we could ideally, and as I had described it, it is the greedy algorithm. We could ideally say the most stable is the one we'll select. But that is not the best idea, because this sort of fixes where the rest of the atoms can go. And that it might happen that the rest of the atoms end up either clashing with the protein or end up in places that are totally not going to serve the purpose of binding to the protein. So we use a slightly biased sampling procedure, the mathematics of which we are not going into. But the bias sampling ensures that you are going to more likely and more often pick the atom or pick the position that is more stable, but you are not going to completely omit positions that are less stable. You will obviously not be picking positions that physically clash or positions that are completely not going to interact with the protein. But there will be positions where it is more stronger in interaction and less stronger in interaction. And both will be considered with a weight to each of them. And that weight is given by the computer. The decision is made by the computer immediately using random number generation. Does that answer? Okay. Uh, I assume that answers. So I'll proceed. Mm, So finally, we come to other flavors in drug design. So this is just a short summary of everything else I have not discussed in this presentation in the name of computer-aided drug design. If we already have a known ligand, there are algorithms that can do peripheral modifications, like I had discussed in the case of fragment-based generation as well. That when we make a fragment set and we find a lead molecule, it's not the final molecule. More often than not, you will attempt peripheral modifications, both to improve the strength and to reduce the toxicity. And there are algorithms that can do that as well. And in this case, the generation or the modification is more important. What you add, how you add them is more important. And docking is less important, because more likely the binding pose as we know it is going to be same. The only sampling is going to be for the side chains that we are going to add. Sometimes it is not very rare that you know protein structure, but you don't know its active site. And there are algorithms that attempt to find the active site of the protein. The most blind and brute force way to do it is to take the known ligand and dock it all over the protein. And where it interacts the best is likely to be the active site, assuming that the interaction energy calculations are correct. Because in real life, the most stable position should be where the ligand is most often found, and that better be the active site. There are, however, other protocols that see water accessibility, concavity, and other parameters like that to decide what is the active site. They're not perfect, but they're quite frequently good, which are again we have not discussed in this, but they exist. And there are many algorithms which use machine learning or artificial intelligence to design the de-novo inhibitors. So in de-novo drug design, a completely new branch that is recently even more popular is machine learning or artificial intelligence based. So we have looked at fragment based, atom by atom based, but there's another way to do it, and that is using machine learning. And this is very, very potent, especially for cases where you know a lot of molecules which already bind, but you want to find a better binder than either all of them, or you want to find a binder for a particular purpose. And in those cases, machine learning and artificial intelligence definitely do a good job. Finally, there is a lot of scope for improvement. So why is computer-aided drug design not, solving everything? And there are a lot of pitfalls, and we will look at them immediately in this slide. So firstly, the most accurate methods are not feasible to be used, because if we are going to look at thousands of molecules, we cannot afford to go for extremely high levels of accuracy, which is why we are using models and force fields, right? The entire force field comes with two parameters for non-bonding interactions, three parameters for non-bonding interactions for a atom. That is not perfect. And the reason we are not able to go beyond that is because each computational program has its limitation. And if you are going to scan lakhs of molecules, you are not going to be able to do sophisticated quantum chemical calculations on each molecule. So what is done otherwise is you use arbitrary empirical scoring functions, get a score, and you take those which are promising to a greater level of or more sophisticated theoretical calculations. And you hope that these models will be accurate. Uh, Again, that also has its own problems, because even to that level, in the end, it is all modeling. And in a computer, modeling does have its weaknesses. But more recently, or even at least quite frequently, when used sophisticated algorithms are fairly able to reproduce experiment results quite closely. Molecules which are predicted by computer may not be easy or cheap to synthesize, as I have discussed. Other than finding a way to synthesize them, assuming there is no way known till now, it is very likely that molecules predicted by computer are not going to be easy to synthesize. And this is especially important for drugs, because drugs are going to be something that need to go to finally a common man, almost every individual, right? And depending on the importance of the scenario, like especially if we are looking at COVID, we are having to give vaccines to all of India. So if you look at the same problem with drugs, it is fairly difficult to be able to distribute drugs easily if they are costly to synthesize. But that is something a computer will not be able to easily predict. Similarly, predicting toxicity is challenging. Again, machine learning is making good dent in this problem, but we are not there yet. And if we manage to overcome these difficulties, we can, in theory, greatly boost the rate of drug development. And with that, these are the references. I presume Science Club will be sharing the slides. The links are not may not be printed completely here, but you can click them and go. That's it. Thank you. Questions, if any?
Does the fragment drug design give some hint on retrosynthesis of drugs?
Um, it is a question worthy of thinking, but I would say no, and I have a reason for that. That is because the restrictions on how the fragments can be joined in a computer are much more looser than you can do in real life. For example, this is might not be easy to do in. I'm not sure. I'm not a synthetic chemist, so I have no idea if this is easy to do. But a lot of the bonds just involve removing two hydrogens and connecting them by a bond. Now, true synthesis in physical sense, that might not be a very easy step to do like a computer does it, but definitely they should be easier to synthesize than a completely ad hoc generation atom by atom. That I think is true, but not by a great margin.
Hey guys, I have a suggestion.
Yes, sir.
No, I'm suggestion to Science Club basically.
Acha, okay.
So the
Yes,
thing
sir.
is that I don't know why you guys are shy about asking questions, because I can tell you that when I was a student, we used to have similar club in IISc, which used to run in the evening after dinner, and there were no faculty. So if you are being shy just because I'm there, then I can leave that meeting. But ideally, it is a forum for you to ask all sorts of stupid questions. Even if you don't know anything, if you are curious about something, just ask away, right? Because your friend is giving a talk, and you are all at the same level. You can teach at the same level, you can think in the same level. So it's just my suggestion that and another thing is that forget about this style of writing questions in the comment. You can write it, but ask yourself. Try to switch on the video like I'm doing now, so that we can see the face and you can ask questions. Feel free, and remember, asking questions will invoke more questions. Like you will be able to open up and ask. So, and Science Club, because you like science, that's why you made the club. So I would suggest that feel free. If you may be shy asking questions when a faculty gives a talk, and I'm not talking about like some of you of course ask questions. I'm saying in general. But here you should shed away all sorts of shyness. Okay. So with that, I think I will leave the meeting. Feel free and ask questions. And then Sreyas, thanks for giving a good talk. Okay. I think you explained really well.
Yes, sir. Thank you, sir.
Okay, I'll leave.
Thank you, sir. Yeah, you guys heard him, and I've told this before too. Feel free to ask questions. Okay, Kilan, can you like unmute and just ask that? You typed a pretty long question.
Okay, yeah. So In the earlier talk, you mentioned the Lipinski's rule of phi. It's an empirical way. So, is there any intuition behind that? Like, what could be the reason behind these rules?
Okay,
Like,
so
I don't understand why having a greater partition coefficient, too many hydrogen bonds. Why would it be a problem?
okay, so for Lipinski's rule of phi, I have some idea, but there are a lot of empirical rules which do not make obvious physical sense because it is more some these I can explain right now. I will do that, but in general, some rules are because they are just statistically more observed in drugs that work, and they don't really have a good reason. People believe that they work because the most of the drugs that have been found either by a computer or in real life by proper like doing actual chemistry have these properties. As for Lipinski's rule of five, I know the basic idea behind why you want less hydrogen bond donors or acceptors, and that is because when you have a ligand that is going to go and bind to a protein, you need to remember that the entire system is aqueous. Having an extremely polar molecule, especially with hydrogen bond donors and acceptors, a much better, which is the best hydrogen bond donor in an aqueous solution, water. So the ligand is most likely, if it has a large number of hydrogen donors or acceptors, it is very likely going to go into water rather than stay in the bound to the protein. And that is not good for us because we want it to stick to the protein and disable the protein permanently, or at least long enough so that it doesn't matter anymore. As for the lesser molar mass, I think it is to do with the cellular permeability, but I think maybe biology people might be able to answer that better. Same with the optimal water partition coefficient. The more polar molecules are not allowed to enter easily, the less polar molecules have problems with the cell membrane because they directly interact or something. I am not extremely sure, but these two have to do with being able to enter the cell and being less toxic.
Oh, okay. Thank you.
In the slide of geometrical optimization,
Hmm.
so finding that geometrical the energy minima, is it like a Monte Carlo simulation are you doing?
So there are multiple ways. The way I was talking about this is a proper what do you call mathematical gradient descent level of optimization. They can be level different ways to do it, but it is not Monte Carlo in the sense that it is not going to find the global minimum. It is going to find the closest local minimum or the local minimum that follows the closest gradient. There are Monte Carlo, and if you want, I have a slide on that as well. But that is not used for geometric optimization. That is used in the generation of different poses during docking itself.
Oh, okay. Now got it.
Hmm. So what docking basically does is it generates positions and it makes. I think I might as well tell you this because it is an important point, and I was thinking maybe I should. Let's get to docking. Hmm. So this is basically what docking does. It takes a random position near the active site and makes a few random modifications to the ligand geometry, and then it depends basically on whether the recomputed score is better or worse. Now, ideally, a proper gradient descent, it would only keep the modification if it is better, but Monte Carlo will allow you to keep a worse modification probabilistically, and that is what I mean by Metropolis Monte Carlo approach. And this is basically the idea of Monte Carlo simulations. So you have a system at this energy level, and this, let's say that you want to find this global minimum. If you have only one dimension that you can traverse, your only way is to go to this unstable position first and then go here. So if you are going to do gradient descent, there is no way you are going to find this minimum. You are going to slip down the gradient and come here, and you will always find only this minimum. But docking is not going to do that. Docking is going to stochastically accept these random moves little by little, and there is a finite probability. And if you have a larger number of moves, you can mathematically show that the probability eventually tends to one as the number of moves tends to infinity. And if with a sufficiently large number of moves, it will be able to cross this threshold with this probability.
So to go towards that global minimum, shouldn't you incorporate some momentum also in your
No,
calculation?
no. So that is different. Momentum. The problem is that even if you incorporate something called momentum, there is energy conservation. If I'm going to start here, no momentum is going to take me to an energy potential which is higher than where I started. Momentum only is going to be that Galileo's thing, right? If you have this, right? If this is your energy profile, if you start here, your ball is only going to climb up till here. If this is going to be taller, there is no way that even if you keep momentum, that is going to cross this barrier because energy conservation. So Monte Carlo
Oh,
is better than keeping momentum.
okay. So, okay.
So, okay, I've got a question.
Mhm.
The force field equations,
Mhm.
do you use them even in geometry optimization? Because the only geometry optimization I know is by using self-consistency, like in DFT calculations. But
DFT calculations, or even if you do hard reform, either of those calculations, they are very rigorous and they are very accurate. This is force fields are in no comparison to hard refork or even DFT or hard refork calculations, but they are a good classical approximation to as far as you can get, and the difference is usually negligible, especially if you are going to use it for computing interaction energies. The difference you'll actually see more in the partial charges. And yes, they are used for the optimization to answer your question. Let me just get there in a minute. Uh, but not directly. So basically, this is not going to be used in the optimization. What you are going to use in the optimization are going to be these. You know the bond lengths, bond angles, and dihedrals, and you know the force constants. So you effectively know the force acting on each atom for any conformation of the molecule, because you know what is the difference from the equilibrium length, you know the difference from the equilibrium angle, you know difference from the equilibrium dihedral, and so you know the force constant, so you can calculate the force on each atom and have it slowly perform a gradient descent along those forces to get the optimal molecular configuration.
okay, so this is a more classical mechanics based approach
This
compared
is
to.
completely classical mechanics based. The quantum mechanics has already been done by whoever has parameterized the force field. So, like I said, we use force field parameters, right? How do we get those force field parameters? They are performed using semi-empirical quantum mechanical calculations, very pretty rigorously. But once we have them, we don't repeat the calculation, which is why there is a slight error. But we are willing to overlook it because we are going to look at a large number of molecules, and doing it for each one is not possible.
Yeah, okay. So, any more questions, guys? Okay, if there are no more questions, we can close this. That's why. Okay, so I'm guessing there are no more questions. Uh, Thank you everyone for attending this, and thanks Reyes for explaining this in a very nice way. You are actually a pretty good speaker.
Okay, I didn't feel so, but thanks.
Okay, so then I'll start. Thank you guys. Yeah, we'll end this now.
Yeah. So
Sure.
anyway, while you're leaving, feel free to mail me if you have any more questions and you don't want to ask right now, or if you think of them later.